the second edition. WCNTDA 2019 has been held physically. Fariha was also present. She was the MC for that session. She also presented in that session, right? And now she is the main presenter for this session. So we are progressing. So I hope in future, maybe 2023, all the students attending will later on be presenter and it will progress and continue on, right? Inshallah. So Dr. Fariha, I think I can call her doctor because examiners have passed her, did her PhD here at UKM. Under Prof. Salmi, and I'm also co-supervising with Dr. Munira and Dr. Almi. She did her undergraduate degree also in mathematics at USM and master at UKM also, right? A master at UKM also and continued PhD studies at UKM. So all those aspiring students, I think they can also ask you about continuing PhD, some sharing experience in that respect. Right, Fariha?
Boleh. Yes.
Yes. So therefore, without further ado, I invite her. Buka majlis dulu. Okay, so we open the session with some meditation for non-Muslim and recitation of Al-Fatihah for Muslim. With that, silakan Fariha.
Okay, so let me share my slide. Okay, can you see the slide, Dr. Fatima? Okay, so let me introduce more about myself again. Let me introduce again myself. My name is Fariha. I'm actually a student of Prof. Salmi that do research in the topological data analysis. So actually, I just finished submitting my hardcover thesis just last week. So currently, I'm waiting for the official letter that saying that I'm officially graduate from PhD. And I would like to mention that I'm actually received the scholarship under USM, which is under Academic Staff Training Scheme (ASTS), or in Malay it will be Rancangan Latihan Kaki Tangan Akademik RLKA. Okay, so today I'm going to talk about hierarchical clustering and topological data analysis. So I'm going to divide the talk into three parts. The first part, I'm going to talk about the hierarchical clustering. Second part, I'm going to talk about topological data analysis. And the last part, I'm going to talk about the combination of hierarchical clustering with topological data analysis. Okay, yesterday Dr. Aftar have already talked about cluster analysis, and there are several methods of cluster analysis. But today I'm going to focus on the computations of hierarchical clustering, the calculation behind that involved in the hierarchical clustering. But I would like to mention that I'm not really an expert in the cluster analysis. I also received a lot of advice from Dr. Aftar since he is my internal examiner actually, and he gave a lot of guidance and advice during my viva to perform the cluster analysis properly. So, but today I'm going to focus on the basic concept of the hierarchical clustering and simple calculation for you to understand more about the hierarchical clustering. So, okay, what is actually cluster analysis? So, cluster analysis is a useful method to partition object from data set into different groups or known as cluster, and objects with similar information are placed into the same group and are kept distinct from one another. So, there are several methods of cluster analysis. So clustering method can be categorized either in hierarchical or non-hierarchical. So for hierarchical, there are two types, will be agglomerative or divisive. For non-hierarchical, it can be model-based clustering, density-based clustering, or partitioning clustering. But today, I'm going to focus only the hierarchical. cluster analysis. So the term hierarchical is actually means that the process of clustering with clusters that are grouped in each step consisting of clusters that are previously clustered. And the agglomerative means that each observations, when I'm going to use the pointer, so there's a point. Okay, for the agglomerative one, each observation starts as singleton cluster and will continually cluster together until it ends up with a single cluster containing all observations. So the agglomerative hierarchical cluster analysis, also known as the bottom-up approach, and the opposite for the agglomerative hierarchical cluster analysis will be the divisive hierarchical cluster analysis. So the divisive means that all observations start in one cluster and continually separated until it ends up with singleton cluster, also known as the top-down approach. Okay, so the output of the hierarchical clustering will be in the dendrogram. So dendrogram is actually a tree-like diagram that records the sequence of merge or split between clusters. So the dendrogram can be in the form of the first figure or it can be in the form of second figure. But the common visualization that you will be find will be the second figure. Okay, let's take a look at basic concept of the hierarchical clustering to the sample example. Okay, let's say you have a data set, you have observation object A, B, C, and D. So you would like to cluster the object A, object B, C, and D. So for the hierarchical agglomerative cluster analysis, which is the bottom-up approach, we're going to start from the bottom to the up. So at the bottom of the dendrogram, the four objects will form a four singleton cluster. So the first cluster consists only object A, second cluster consists of object B, and the third cluster consists of object C, and so on. So at the second level of the dendrogram, another cluster will form. So the object that close to each other is going to form another cluster. So in this case, object A and B form another cluster. And again, the hierarchical agglomerative cluster analysis process will be continue. And again, the close object that close to each other is going to form another cluster, until finally a single cluster containing all the observation is produced. So this is the final level for the dendrogram in the agglomerative hierarchical clustering. And the opposite for the agglomerative hierarchical clustering will be the divisive hierarchical cluster analysis. That will be the top-down approach. So we're going to start from the top to down. So from the top, we're going to start from a single cluster containing all the observation and it's going to be separated for into the two clusters that consists of object A, B and object C, D, and again it will be separated into the singleton cluster. Okay. But today, I'm going to focus on hierarchical agglomerative cluster analysis since it is the common one that people use. And the step for the hierarchical agglomerative cluster analysis are known as HACA, the simple form. So in the step 1, n singleton cluster are formed from n observation. So if you have 4 observation, 4 singleton cluster will be produced. So if you have 10 observation, then 10 singleton cluster will be produced. So in the step 2, we're going to compute the dissimilarity distance. So dissimilarity distance between the observations is calculated in step 2. And in the step 3, the two clusters with the smaller distance are merged into new cluster. And in the step 4, new dissimilarity distance between the new cluster and each of the old cluster are calculated. So at this stage, we require a linkage to connect between the groups or between the cluster. And in the step 5, the step 3 and 4 are repeated until a single cluster containing all observation is produced. Okay, so there are 2 things that you need to determine in the HACA process, which is the dissimilarity distance. And then the linkage. So what is the dissimilarity distance that you want to use? And what is the linkage that you want to use to connect between the groups, between the cluster? Okay. So there are several types of the dissimilarity distance, but the common one that being applied in the HACA process would be the Euclidean distance. Other example of the dissimilarity distance can be Mahalanobis distance, Minkowski distance, or Manhattan distance. But today I'm going to focus on Euclidean distance only, since it is the common one. And for the linkage, there are several types of linkage methods. The common one will be the single linkage, the complete linkage, and the average linkage. That's a typo. This one is the average linkage. And for the single linkage, the distance between the group is determined by the minimum distance between pair of objects, one in one cluster, one in the other cluster. And for the complete linkage, the distance is determined by the maximum distance between pair of objects, one in one cluster, one in the other cluster. And for average linkage, the distance is the average distance between the pair of object, one in one cluster, one in the other cluster. Okay, so don't worry too much about the formula of the linkage. I'm going to show you through the simple example how the linkage works. So let's start for the example HACA for the single linkage. So let's say we have a data set. We have a data set with object A, B, C, D, and E. So we have variable V1 and variable V2. So in the step 1, the n-singleton cluster are formed from the n observation. So since you have 5 objects, so we're going to have a 5 singleton cluster. So we're going to record in a dendrogram at the first level will be the singleton cluster. So the 5 singleton cluster consists of each object. Okay, in the step 2, we're going to compute the dissimilarity distance between observation. Okay, we're going to compute the dissimilarity distance using the Euclidean distance, which is the usual one. I assume that there are a lot of you that have known about the Euclidean distance, but I'm still going to go through the Euclidean distance step by step. So let's say we want to compute between the dissimilarity distance between the cluster 1 and cluster 2. So the cluster 1 consists of object A and cluster 2 consists of object B. So the element of object A will be equals to 1 to 1, which refer to the variable V1 and variable V2. And for the object B, the element will be 1, 2, which refer to the variable V1, 1, and variable V2, 2. Okay, so we're going to use the formula of Euclidean distance, and we're going to compare distance between the cluster 1 and cluster 2, which is the object A and object B. So the first element will be equals to 1 minus with the first element of object B. So 1 minus 1 power of 2, and we're going to plus with the second element of object A will be equals to 1, and the second element of the object B, we're going to minus between the two elements. So taking the square roots, we're going to get the distance between the object A and B will be equals to 1. So the distance, we will fill the distance in a dissimilarity matrix. So dissimilarity matrix, the row and the column will be your observations. So in this case, the distance for between the object A and object B will be equals to 1. So we're going to fill in the dissimilarity matrix, and the distance between the same object, distance between A and A will be equals to 0. So next, if you want to compute the distance between the cluster 1 and cluster 3, that will be cluster 1 consists of object A, cluster 3 consists of object C. So we're going to compute the distance between object A and C, and we're going to repeat the same step. So the first element of the object A will be equals to 1, the first element of the object C will be equals to 3. So we're going to minus the two first element, plus with the second element. So we're going to minus between the second element of object A and second element of object B, and we're going to get the answer will be equals to 2. So we're going to fill the dissimilarity matrix, and we're going to get the dissimilarity matrix 1, the first dissimilarity matrix. So I intentionally left this space as a blank space because this space, the answer for this space is actually the same one to the left side. So I'm just going to focus on the left side, since the right side is just the equal answer. Okay, so now in the step 3, the two clusters with smallest distance are merged into new cluster. So we're going to ask the question on the dissimilarity matrix 1. So what is the smallest distance in the dissimilarity matrix 1? So the smallest distance will be equals to 1, which is the distance between A and B. So since distance between A and B is the smallest one, so we're going to combine object A and B in one cluster. So we're going to record in the dendrogram, we're going to link the object A and B, which means that the object A and B form another cluster. Okay, so we already have the first cluster in the dendrogram. Next, we're going to proceed with the step 4. In the step 4, the new dissimilarity distance between the new cluster and each of the old cluster are calculated. So linkage is required in this step. So in this step, we're going to use the single linkage. So refer back to the dissimilarity matrix 1. We're going to compute the new dissimilarity matrix between the new cluster and old cluster. So the new cluster here will be cluster that containing object A, B. Okay, so we're going to compute the distance between object AB to C, AB to D, and AB to E. So we're going to compute using the single linkage. For example, we want to compute distance between AB to C. So distance AB to C is actually equals to the minimum, which refer to the single linkage. So which is the minimum between distance A to C and B to C. So distance between A to C, B to C will be equals to the minimum. Okay, let's refer back to the dissimilarity matrix 1. So distance A to C will be equals to distance A to C will be equals to 2. So the answer here will be equals to 2. So distance B to C, refer back to the dissimilarity matrix 1. Distance B to C will be equals to 2.24. So the minimum is between 2 and 2.24 will be equals to 2, and we will fill the answer in the new dissimilarity matrix. Okay. Next, for the next example, let's compute the distance AB to D. So distance AB to D actually equals to minimum distance A to D and B to D. So distance A to D, refer back to the dissimilarity matrix 1. Distance A to D will be equals to 5, and distance B to D will be equals to 5.1. So the minimum between 5 and 5.1 will be equals to 5. So we're going to fill in the new dissimilarity matrix, the distance AB to D equals to 5. So we're going to compute the rest of the dissimilarity distance between the new cluster and old cluster, and we're going to fill the rest of the dissimilarity matrix, and we're going to name it as the dissimilarity matrix 2. So this is your second dissimilarity matrix. Okay, next, in the step 5. So in the step 5, step 3 and 4 are repeated until a single cluster containing all observation is produced. So the step 3 is actually two clusters with smaller distance are merged into new cluster, and in the step 4, new dissimilarity distance between the new cluster and each of the old cluster are calculated. So okay, we're going to do the step 3. You have a new dissimilarity matrix, which is dissimilarity matrix 2. So we're going to ask the same question. What is the smallest distance in the dissimilarity matrix 2? So the smallest distance will be equals to 1.41, belong to the distance between object C and E. So object C and E will form another cluster, and we're going to record in the dendrogram. So we're going to link object C, E in one, which means that it forms another cluster. Okay, in the step 4, we have to compute again the dissimilarity matrix. So we're going to name it as the similarity matrix 3. Still, we're going to refer to the first dissimilarity matrix, and we're going to compute the distance between AB to CE. So distance AB to CE is actually the minimum. Distance A to C, A to E, B to C, and B to E. So we're going to calculate distance between AB to CE, and we're going to take the minimum of the distance between two groups, and the minimum will be equals to 2. So we're going to fill in the dissimilarity matrix 3 as value 2. Okay, next we're going to compute the rest of the distance. Distance between object AB and D will be equals to 5. So we're going to fill in the dissimilarity matrix 3, and distance CE to D equals to 2.24, and the answer here will be equals to 0.24. So we have complete the dissimilarity matrix 3, and again we have to ask the same question. What is the smallest distance in the dissimilarity matrix 3? So the smallest distance will be equals to 2, which is belong to the distance between object AB to CA. So object AB and CA will form another cluster. So we're going to link the object AB to CA here in the dendrogram, and we will continue the process of hierarchical of HACA. Okay. So next, this is the final dissimilarity matrix that we're going to compute. We're going to compute between this distance between the object ABCE to D. So object distance between cluster that consists of object ABCE to D is actually equals to the minimum distance A to D, B to D, and C to D, and E to D. So refer back to the dissimilarity matrix 1. Distance A to D will be equals to A to D will be equals to 5. Distance B to D, B to D will be equals to 5.1. And the minimum for all the distance will be equals to 2.24. So we're going to fill in the dissimilarity matrix 4, and the answer will be equals to 2.24. So, okay, we're going to ask the same question again. So, what is the smallest distance in the dissimilarity matrix 4? So, the smaller distance will be equals to 0.24. That is the only distance that we have. So, cluster consists of object A, B, C, E will be combined together with object D. So we're going to record in the dendrogram. So we're going to link the object A, B, C, E with D at the distance of 2.24. Then we have the complete dendrogram, since a single observation or a single cluster containing all the observation has been produced. So that's for the HACA for HACA for single linkage. And next, we're going to see example HACA for complete linkage. Now, for the complete linkage, we're going to consider the maximum distance between the two groups. So, refer back to the dissimilarity matrix 1 that we have computed previously. And the minimum distance will be equals to 1. So object A and B will be linked together, and we're going to record in the dendrogram. So object A, B linked together, and we're going to compute the next distance, which is a dissimilarity matrix 2, and we're going to repeat the process similar with the single linkage. Only the difference, we're going to consider the maximum distance between the two groups. So for example, distance AB to C will be equals to maximum distance A to C and B to C. So distance A to C will be equals to 2. So we're going to write here equals to 2. And distance B to C equals to 2.24. So the minimum between 2 and 2.24 will be equals to the maximum between 2 and 2.24 will be equals to 2.24. So we're going to fill in the dissimilarity matrix 2, the distance between AB to C equals to 2.24. So next, we're going to compute the rest of the distance between the cluster and between the new cluster and the old cluster, and we're going to fill the dissimilarity matrix 2, and we're going to ask the same question. What is the smallest distance in the dissimilarity matrix 2? So the smallest distance will be equals to 1.41, which is belong to distance between object C and object E, and object C and object E will be clustered together to form another cluster. So we're going to record in the dendrogram, object C and E is clustered together. Okay. Next, we're going to compute the next dissimilarity matrix. So dissimilarity matrix 3, we're going to compute the distance between object AB to CE, AB to D, CE to D. So distance between a cluster that consists of object AB and cluster that consists of object CE will be equal to the maximum distance between A to C, A to E, B to C, and B to E. So the distance, we're going to fill in the distance based on the dissimilarity matrix 1. Distance A to C will be equal to 2. Distance A to E will be equal to 3.16, and the maximum between the distance will be equal to 3.16. So we're going to fill in the dissimilarity matrix 3. Distance between the object AB to CE will be equal to 3.16. Okay. We're going to fill the rest of the dissimilarity distance between the cluster, and after we have a complete dissimilarity matrix 3, and we're going to ask the same question. So what is the smallest distance in the dissimilarity matrix 3? So the smaller distance will be equals to 3. So object CE and D will be combined together to form another cluster, and we're going to record in the dendrogram object CE linked together with object D at the distance 3, and we're going to have this structure in the dendrogram. Okay, we're going to continue the HACA process and compute the dissimilarity matrix 4. So dissimilarity matrix 4 will be between object AB to CED. So distance AB to CED is actually the maximum. Maximum refer to the complete linkage. So the maximum distance A to C, B to D, B to C, A to E, B to E, A to D, and B to D. So distance between the two groups, and the maximum of the distance will be equals to 5.1. So we're going to fill in the dissimilarity matrix 4. Distance AB to CED will be equals to 5.1. So the cluster that consists of object AB and cluster that consists of object CED will be combined together and form a cluster, a single cluster at the distance 5.1, and we're going to record in the dendrogram. So we already have the complete dendrogram for the complete linkage of HACA. Okay. Now let's continue with the average linkage. So the example HACA for the average linkage, refer back to the dissimilarity matrix 1, and the minimum, the smaller distance will belong to the object A and B, and we're going to record in the dendrogram. Object AB is linked together, and we're going to compute the second dissimilarity matrix. And we're going to compute distance between the new cluster and the old cluster. And at this time, the difference is we're going to use the average linkage. So the single linkage based on the minimum distance, the complete linkage based on the maximum distance, and the average linkage will be the average between the two groups. So let's see how to compute using the average linkage. For example, let's say we want to compute the distance AB to C. So distance AB to C. Now, this is the formula of the average linkage. We have a variable P and Q. The P here will be equals to number of observation in cluster AB. So Q here would be the number of observation in the next cluster, which is the cluster that consists of object C. So here, distance AB to C, the P here will be equals to 2, since the first cluster consists of object A and B. So the number of observation here will be equals to 2. So P equals to 2. So P equals to 2 here. And for the Q will be the number of observation in cluster C. So cluster C, the second cluster consists only one object. So the Q here will be equals to 1. Inserting in the formula, so we have 2 times 1 in the denominator. For the above one, we're going to take the summation. The summation between the two groups, summation of the distance between the two groups. So we're going to take the distance A to C plus distance B to C, and Distance AC, distance BC, we're going to get from the dissimilarity matrix 1. Distance A to C will be equals to 2. Distance B to C will be equals to 2.24. So we're going to take the average. And the answer will be equals to 2.12. And we're going to fill in the dissimilarity matrix 2. Okay. So that's the difference between the single linkage and complete linkage. For here, we're going to compute the average instead of the minimum and the maximum distance between the groups. And next, let's see the next example. Let's say we want to compute the distance AB to D. So similarly to the distance AB to C, we're going to compute the average of the distance A to D plus distance B to D divide by 2, which is referred to the P times Q here. So the P here is 2 and the Q is equals to 1. So distance AB to D will be equals to 5.05, and we're going to fill in the dissimilarity matrix 2. Okay, so we're going to fill the rest of the dissimilarity matrix 2, and we will have a complete dissimilarity matrix 2, and we're going to ask the same question. So what is the smallest distance in the dissimilarity matrix 2? Okay, so the smallest distance will be equals to 1.41, which is belong from the distance C to E. So object C and E will be linked together, and we're going to record in the dendrogram. Okay. Next. Okay, so next we have to compute the new dissimilarity distance between the new cluster and the old cluster. So we're going to compute the dissimilarity matrix 3. So here we're going to compute distance AB to CE, AB to D, and CE to D. So distance AB to CE. Okay, in this case, the P here will be equals to 2. The first cluster consists of 2 observations, so the P here will be equals to 2. And the next cluster consists of object CE. So Q here will be equals to 2. So we have the denominator P times Q, we will get 2 times 2 here. And the above one, we're going to take the summation between the two groups, summation of the distance between the two groups, which is the distance A to C plus A to E plus B to C plus B to E. And we will have this distance based on the dissimilarity matrix 1, and the distance AB to CE based on the average linkage, we will have 2.6. So we're going to fill in the dissimilarity matrix 3. So next, we're going to compute distance between AB to D, and here, the P here will be equals to 2, which refer to the first cluster consists 2 objects. And in the next cluster, only 1 object contained in the next cluster. So the Q here will be equals to 1. So the denominator will be equals to P times Q, so 2 times 1. And taking the average of the distance will be equals to 5.05. And we're going to fill in the dissimilarity matrix 3. And we're going to have distance AB to D equals to 5.05. Next, we're going. Similarly, we will compute this similar way for the distance CE to D, and we will have a complete dissimilarity matrix 3. And again, we're going to ask the same question. So what is the smallest distance in the dissimilarity matrix 3? So the smallest distance will be equals to 2.6. Okay, so cluster that consists of object AB and cluster that consists of object CE will be combined together to form another group. So we're going to record in the dendrogram. So AB, so object AB and CE link together at the distance 2.6. So and form another cluster. Okay, and then we will compute the next of the dissimilarity matrix. And the dissimilarity matrix 4, we have to compute the distance between a cluster that consists of object A, B, C, E to D. So distance between A, B, C, E to D, here the P here will be equals to 4, since the first cluster consists of 4 objects, object A, B, C, E. So the total here will be equals to 4, so P equals to 4. For the next cluster, only 1 object consists in the next cluster, so the Q here will be equals to 1. So P times Q will be equals to 4 times 1, and taking the summation of distance between the two groups, will have the answer will be equal to 3.84, and we're going to fill in the Dissimilarity matrix 4, and the distance between A, B, C, E to D will be equal to 3.84, and this is the only distance that we have in the Dissimilarity matrix 4. So object A, B, C, E will be combined together with object D at the distance of 3.84, and we're going to record in the dendrogram. So in the dendrogram, object A, B, C, E will be linked together with object D at the distance 3.84, forming a single cluster containing all the observations. So this is the complete dendrogram that you have for the HACA with average linkage. Okay. So this is the full result of the HACA result for single linkage, average linkage, complete linkage for the example of data set that I given before. And in this case, we can see that the single linkage and average linkage produce the same result. But this is only the case for data that I provide. In other data, it might be different. Okay, it might be different. And for a single linkage and average linkage, the object A, B will be combined together first, next the object C, E, and then later object A, B, C, E will be combined with the object D. And for the complete linkage, there is different result is produced with object A, B linked together first, and then next object C, E, and object C, E will be linked together with object D, and finally a single cluster consist of all observation is produced. Okay, that is the example for the HACA results. Okay, so now, Dr. Fani, is there any question?
There is one from Zahira. Dia cakap bagaimana jika ada nilai distance yang sama, nilai manakah yang perlu diambil? Yeah, if you have a similar distance, which one would you choose? Yes.
Selalunya dia tak akan sama. Selalunya dia tak akan sama dia, sebab bila kita compute dissimilarity distance, is going to take up to 6 decimal place, I think, and it's really to get a distance that is similar. But if that is the case, either one, in my opinion, either one will be, we can choose either one. I mean, that they are similar, right? They are, the minimum value is similar, right? So we can choose either cluster to, the first cluster to combine together. In my opinion.
I have a follow-up question. You use R, right? So in R, does it have auto setting? Which one it would choose? If the distance is similar?
Or auto setting for the dissimilarity distance or linkage method or what?
Auto setting if is similar.
If similar. No, it's actually the algorithm for the HACA itself involve the minimum one. So the minimum distance is the rule in the HACA process. So if we compute the dissimilarity distance, the minimum distance will be the criteria to choose the cluster. So that is automatically in the HACA algorithm. So there is no auto setting for the minimum one. But actually, for the case of for the question for Zahira, actually, I think it's difficult. I think I never find the dissimilarity distance with the similar value. If you in that case, you will have overlap. Overlap. Data observation with the same information, but usually the observation itself will be in different kind of information. So it's quite quite impossible to have a same distance in dissimilarity distance.
Okay.
So it will have.
Alright, I think
let me know if you have the case where the dissimilarity distance there is a two minimum distance. in this method. Okay.
All right.
Is that
Yes. Maybe Zahira can comment further, and
yes.
maybe she has an example, right? Okay. In
Uh-huh.
the meantime, I think Felix Ohanuba wants to from USM, I think, wants to ask
Yeah,
a
yeah.
question. I have. You can unmute yourself, Felix, if you want to ask. You want to speak because you raise your hand.
Okay. Thank you for the presentation. I have a little question.
Uh-huh.
I want to know where the measurement, the actual distance reflects in the dendrogram diagram.
The choice for distance?
Yeah. How you measure it to reflect in the diagram presented. Yeah.
So can you repeat the question?
Where the values is measured and they reflect in the graph you present. Yeah, for each of the types of a hierarchical clustering.
Do you mean that the
Yeah,
effect
the distances of each, where it reflects in the results. I want to know how you measure it to reflect in the actual figures presented here, because already you showed us the values, the numbers you obtain for each of the types of clustering, hierarchical clustering, like in single linkage. We saw the result in the data. In the other complete linkage, we saw the results. Then I want to know how you reflect those results in the figures here. The distances you measure, how you measure it to reflect. Thank you.
Okay. Oh, I don't have the plot for the data set.
Okay.
Yeah. So we can see from the data set, if we plot the data in the graph, we can see that object AB is close to each other, and object CE is close to each other, and then the far one will be object D. So I forgot to plot the data in the graph so that we can relate the HACA result with the data points. Is that your question? How
Yeah,
we go?
yeah.
Okay.
Yeah. And the scale, yeah.
So if you plot the data set, you could see that object A, B is close with each other. Object C and E is quite far away from object A, B, so CE will be combined together first. And next, object D is the far away. So I forgot to insert the figure that show the position for each observations. And okay, does that answer your question?
Yeah.
So it's highly related to the position of the data itself. So objects that close to each other will be clustered together in observation. So it is highly related to the position of the data itself.
Okay. So you did it manually or you use software?
I use software. Okay, I would like to mention. Actually, I want to mention at the end of the session. But if you need a coding that I use to compute the example in this slide, I could provide to you. You can email to me and I could provide the code that I use. But it will be in the R software. Okay.
All right.
If you need the code, you could email me.
Yeah. Please send your email here. Thank you.
Yes.
Is that the function that you put there? H class?
H class.
That is the function you use in R, yeah? Okay, very good, Fariha. I think a lot of people are interested. So we have a lot more questions here. Here is from Dr. Nazar Safian. Dr. Nazar is from HUKM. He is a Prof Madya of Public Health. He attended WCNTDA 2019 also. And he asked how to interpret the different result between single, complete, average. And this question is related to Aisha's question, which one is the most preferable to get results? And Fatiha's question also, maybe you can give real example when we need to use single, complete, average linkage.
Okay, can I show that later?
Okay,
Just
sure.
after this, okay?
I see.
Okay.
So Fariha has something in store for you. So stay tuned. She will explain later. Thank you for the question.
The question will be how to select the result. It's either for the single linkage or complete linkage or average linkage. Which one is the best we want to choose, right? Okay, so I'm going to show in the next example. Okay.
That's wonderful. So I think these questionnaires are very advanced because they already know what you are going to show in the next slide. So all yours, Fariha. Do continue.
All right. Okay, let me continue. Okay, so I want to put some remark here. It's about single linkage, complete linkage, and average linkage. And okay, for the single linkage, it tends to produce irregular shape of cluster structure, and the cluster can appear spread out. It means it's not organized, and cluster may not be compact, and it can sometimes produce cluster where observation in different cluster are closer together than to observation within their own cluster. So the example that I provided before consists of observation about only five observations. But if you have a lot of number of observation, for example here, going to show you for example here I have 52 observations. I have 52 observations. You can see clearly the difference between the single linkage, complete linkage, and average linkage. And for the single linkage, the structure of the cluster is a bit in irregular shape. Okay. Now, for the complete linkage tend to produce a compact cluster with equal diameter, maximum distance between the object. So the linkage usually produce tighter cluster than a single linkage, but this tight cluster can end up very close together. And it can be severely distorted by the moderate outliers. So if you see in the next figure, by comparing the dendrogram for the complete linkage and single linkage, it can be seen that the complete linkage produce a well-separated cluster compared to the single linkage. And it is clear to see the cluster that distinguish each other by using the complete linkage compared to the single linkage. And for the average linkage, it tends to join cluster with small variance. It's slightly biased to producing cluster with the same variance and intermediate between single and complete linkage. So for the average linkage, it is in the middle actually, middle of the result, single linkage and complete linkage. But if you see the average linkage, we still cannot see clearly the distinct cluster based on the average linkage compared to the complete linkage. So back to the question that Dr. Fatima have told me before, I would say, based on my experience, I would say complete linkage produce a much better result, which is more well-separated cluster, and we can see clearly the distinct between the cluster compared to the single linkage and average linkage. So back to the question that Dr. Fatima asked before, I would say comparing between average linkage and single linkage and complete linkage, I would say the complete linkage is the best one to select. But still, I would like to mention that the cluster analysis is the unsupervised technique. It is an exploratory data analysis, and you have to refer back to your subject expertise. Maybe single linkage is more suitable for the result that you want to achieve. Maybe average linkage is the one that's suitable for your for the objective that you want to achieve. Maybe the complete linkage, but I cannot say that this is the right linkage, this is the right distance that you have to choose. You have to explore and relate the result with your subject expertise. Okay, maybe you have to have something expected result that you want to get, and you have to see which one is the dendrogram suitable for what the result that you want to achieve. Okay, Dr. Fatima, is that answer the question before?
For me, I think okay, but we request that the participant maybe can comment further if they have further question or whether they're satisfied or not. But you can continue on and then maybe we can address it
Okay.
at next
All
week.
right.
Thank you, Fariha.
Okay. Thank you, Dr. Fatima. Okay, determine number of cluster. So this is the most popular question when we perform the HACA, because for HACA we don't need to state what is the number of cluster that we want to get. There can be multiple of cluster that we can get. So for determine number of clusters, so number of cluster form are determined by cutting the dendrogram at certain level. So this is the basic approach. The basic approach is we cut at the dendrogram and that is your cluster. For example, HACA for single linkage here is the dendrogram. And if we cut at the blue line, so the y-axis will be the dissimilarity distance value. If we cut at the blue line, we're going to get 1, 2 cluster, 3, 4 cluster. So the total of cluster, if you cut at the blue line, will be 4 cluster. And if you cut at the red line, you're going to get 1, 2, 3 cluster. And if you cut the dendrogram at the green line, you're going to have only 2 clusters. So that's the basic approach. You cut the dendrogram, then you get the number of the cluster. But this is the basic approach. This is the basic approach. You cut the dendrogram, you get the cluster. But there is formal method that you can use to guide you to get the cluster that you want. So I'm going to show you the basic one, the most basic one. Okay, cutting the dendrogram at certain level defines a partition such that cluster below that height are distant from each other by at least that amount, and the appearance of the dendrogram can thus informally suggest the number of clusters. So we cut at the certain level in the dendrogram. That will be the informal way to get the cluster. But by applying HACA, the goal is to get the cluster that is well separated and distinct with each other. So that will be our main objective when we want to cluster the object. We want the object to be separated, to have the groups that belong to this object, the groups that consist this collection of the object. So we want it to be well separated. And the criteria that we can use to choose the number of cluster is based on the large change in dissimilarity distance level are taken to indicate the base cut. So we're going to visualize the dendrogram. We're going to visualize the dendrogram and see where is the light change of dissimilarity distance level. And we're going to choose that from the bar plot. So we're going to plot the bar plot between the number of cluster and dissimilarity distance. So based on the bar plot, we're going to observe the largest change of dissimilarity distance between the number of cluster in the bar plot, and the minimum number of cluster that could be chosen will be 2. So this is the minimum number that you will want to be choose. We're not going to choose the minimum number cluster as 1. So because that will be produced the singleton cluster. So the minimum number will be 2. So the total possible number of cluster that could be produced will be n-1. So if you have 5 observations that you want to cluster, it would the total possible number cluster that you could have would be 5 minus 1, 4. So you could have a 2, 3, 4 cluster. Okay, so determine number of cluster. Let's plot the bar plot. So the bar plot, the x-axis will be the number of cluster, and the y-axis will be dissimilarity distance. So if we want to have only 1 cluster, the dissimilarity distance here, where the cluster combine together. So for example here, cluster AB will be combined together at the distance 1. So the bar plot here would be equals to 1. So 4 here refer to the number of cluster that could produce if we cut the dendrogram between the between the distance value. For example, if we cut at wait, let me use it back. If we cut at here, then we have 1, 2, 3, 4. So 4 cluster here at the distance between here. If we cut at 3 here, between distance between 1.4 something and 2 something. So if we want to have a 3 cluster, then we will have to choose the distance between, I think this one is 1.41, between 1.41. So what the criteria that we're going to see is the large jump between the distance value from one cluster to another cluster. So for example, from one cluster to 2 cluster, there are small jump here. But for 2 cluster, between the 2 cluster and 3 cluster, there are large jump here, and from cluster 3 to 4, there are quite medium one jump here. So the optimal number that you could choose would be cluster 2, cluster 3 or 4, refer to the large jump here. So the large jump here actually indicate the separation between the cluster. It means that but from the dendrogram, we can see that it is the cluster is well separated at when you choose the distance between here. Compare if you cut at the dendrogram here, since it's show a small distance here. So it will be preferable that you choose to cut the distance from here to which is between cluster 2 to cluster 3, since the large jump show between the cluster 2 and cluster 3. So you could cut the dendrogram at here or at here. So okay, so that's the basic approach that to determine the number of clusters. But this is the most basic one. There is a formula one. For example, Dr. Aftar had mentioned yesterday, based on the cluster validity index, rank index, variation of information, motion information, such that, or you could use the dynamic tree cut to determine number of cluster. But I show you the most basic one. The most basic one, you visualize your dendrogram and see where the cluster is well separated. The most that show that the cluster are distinct with each other, and so on. So this is the basic one, the basic approach that you can use to guide you to choose the number of cluster. But again, cluster analysis is an unsupervised technique. If you choose a certain number of cluster, you still have to refer back to your subject expertise. So maybe the cluster that you choose is not suitable for the result that you want to achieve. So it's still you have to have a number of cluster that you expect to get. But this approach is just, you can use it as the guidance to choose the number of cluster. Okay, so next, for the single linkage. Now for the single linkage, let's see where is the large jump. So the large jump will be so between cluster 1 to 2, and next will be between 2 to 3, and this will be the small jump. So the optimal one, you could choose 2 cluster. You could have the 2 cluster to produce, or you could have the 3 cluster. But judging from here, I will choose the largest one. So the largest one from 1 cluster to 2 cluster. So I'm going to choose 2 cluster. So I'm going to cut at this distance. So you can see that from your dendrogram, from the first cluster to the second cluster, the distance quite large here. We show that the group is separated, well separated at here, and compared to the next one, which will be the distance from here to there. Okay. So all right. Okay, okay, doctor. Fatima. Is there any question before I proceed with the part 2?
Okay, Fariha, I think there is no further question for now. We can continue. It's only part 2, Fariha. You got 3 parts yet.
Why? What time
Yeah.
now?
Almost 1 hour. So I think you better continue. Please do.
Alright,
Thank you.
okay. Okay,
Ni
I'm going
kena
to...
buat,
Okay.
Fariha kena buat satu hari punya bengkel ni.
Tak apa. Future.
Alright.
InsyaAllah.
So, okay, I'm going to proceed with the part 2, which is the topological data analysis, which is my PhD research. Which is my PhD research, which is in the topological data analysis. Okay. So, topological data analysis, or TDA. So, TDA is used to study the shape of data by extracting qualitative feature of where is the pointer? Qualitative features of data known as topological features. So TDA concerned with shape of data. So TDA concerned with shape of data instead of the quantitative value in the data set. So the shape here is described by the topological features. So the main tool in the TDA will be persistent homology. So the persistent homology, it is based on the homology theory in algebraic topology. Okay, so the example of topological features here, you would be like a connected component, which is the 0-dimensional homology, the whole, which is the 1-dimensional homology, and void for the 2-dimensional homology. So okay, the example of the connected component, for example here, let's say you have 4 data points. So the 4 data points is actually the 0-dimensional homology connected component. So 4 points, 4 connected component, 4 0-dimensional homology. And if you have data set where your data, certain of your data points connect with each other, we're going to have 1 connected component, 2 connected component, 3 connected component. So 3 0-dimensional homology. So in this case, if you have 4 data points that connect with each other, forming like a loop, so we're going to have 1 connected component and 1 hole. So 1 hole here refer to the loop with the empty space inside, empty region inside. So we have a loop and empty space inside in the middle. So for the void, let's imagine the sphere shape. So for this case, we're going to have 1 connected component, 1 void. So 1 void here refer to the enclosed region with the empty space inside. So you could think object ball too. The ball also have 1 connected component and 1 void. So that's the example of the topological features. And the tool in the TDA will be persistent homology. So persistent homology is used to study the qualitative features of data that persist across multi-scales. It is robust to the perturbation of the input data, independent of dimension and coordinate, and provide a compact representation of the qualitative features. And the type of data set that can be studied using persistent homology include the finite metric space, digital image or network or other kind of set of data. And the application of persistent homology will be detecting financial crisis, identifying a subgroup of breast cancer, early detection of bifurcation and chaos in complex system. So there are a lot of application of persistent homology. Okay, so in persistent homology, the process begin with construction of simplicial complex on data set. So a simplicial complex is constructed based on the simplices. So simplices, this is an example of the simplices. The 0 simplex will be the point or vertex. 1 simplex will be line or edge. 2 simplex will be the triangle. You have a 3 point that connect with each other. We're going to put a triangle here. And for the 3 simplex will be the tetrahedron. So the combination between the simplices will be a simplicial complex. So if you see the example, the simplicial complex is the combination between the edges, between the point, between the triangle, between the tetrahedron. So that's an example of the simplicial complex. Okay, the basic process to construct the simplicial complex in the data set. So we're going to draw a circle for each data point with each of the data point act as the vertex in data set. So the process of persistent homology, let's say you have 4 data points. So 4 data points, we're going to draw a circle with epsilon as the radius. So so at this stage, we're going to have 4 zero simplex, because the zero simplex is actually the points. And at this stage, we're going to have 4 zero simplex. So when we increase the epsilon until 1, the circle start to appear because the radius become bigger. So the circle also become bigger. And then if we increase the epsilon value to epsilon equals to 4, if the circle intersect with each other, we're going to draw a line connecting the 2 points. And the line is actually referred to the 1 simplex. It does not necessary to the circles to be intersect. If their circle just touch with each other, we can draw the line that connect between the 2 points. And if we increase the epsilon value until 5.66, and more points will be connect with each other. For example, point here connect with point here, and we're going to have a 2 simplex which fill the previous simplicial complex. Okay. Now, there are many types of simplicial complex, such as a catch complex, Ritz complex, and a witness complex. So, Ritz complex consists of simplices with vertices and diameter at most epsilon. So, in other words, a simplex is included in the Ritz complex if each pair of the vertices in the simplex is at most epsilon apart. Now, we will include the simplex in the Ritz complex if the distance between the 2 pair of points at most epsilon apart. So the easiest way to know when is the point in the data set will be connect with each other is to compute the distance between the points. So usually the distance will be the Euclidean distance that we have computed before. So for example, here is the matrix that consists the distance between the points. Distance 1, distance 0.1 to 0.2 will be equals to 4. So distance 1 to 2 will be equals to 4. Distance 1 to 3 will be equals to 5.66. Distance 1 to 3 will be equals to 5.66. So from the matrix actually give you the information, the diameter of the points. So we could refer the epsilon value here as the distance that we have computed here. Okay, so for example, let's start with your 4 data points. Let's say you have 4 data points. At the epsilon equals to 0, we're going to draw a circle with radius equal epsilon equals to 0. And when the radius increase, when the epsilon value increase, the circle also start to growing up. And until the epsilon equals to 1 will be increased until epsilon equals to 4. From the metric here that we have computed before, we know that 0.1 and 0.2 connect with each other at epsilon equals to 4. So we're going to draw a line between 0.1 and 0.2. And and in the matrix 2, 0.1 and 0.4 connect at the epsilon equals to 4. So at the epsilon equals to 4, we're going to connect the 0.1 with 0.4. And similarly with the 0.2 and 0.3 and 0.3 to 0.4. So we're going to have connected component here, your data points that already connect with each other until the epsilon keep increasing until epsilon equals to 5.66. So at epsilon equals to 5.66, the 0.1 and 0.2 connect with each other, 0.1 and 0.2 connect with each other, 0.2 and 0.4 connect with each other at 5.66. So we're going to draw a line here. So when we draw a line in the middle, the 2 simplex will be appear. Okay. Now, the output of the persistent homology will be in the barcode and persistent diagram. So the thing that we're interested in study the topological features is actually the birth and dead points of the topological features. And the birth and dead point of topological features are recorded based on the construction of Ritz complex. So refer back to the construction of Ritz complex that we have before, and at the first step epsilon equal to 0, the 4 zero simplex is actually the 4 connected component. So the 4 connected component, we will say this is the birth point of topological features connected components, and we're going to draw align at the barcode. So 1, 2, 3, 4 line here, which refer to the 4 connected component. So when the epsilon increase until epsilon equals to 1, the line also keep increasing. It will be increasing. It will be keep increasing parallelly with the increasing of the epsilon value until epsilon equals to 4. So at epsilon equals to 4, the points start to connect with each other, and point 1 and point 2 connect with each other, causing the dead of one connected component. So that's why the line here stop here. So we're going to say the dead point for this connected component is at epsilon equals to 4. And when point 2 connect with point 3, it will cause another connected component to be dead. And next, point 3 and point 4 connect with each other, it will cause another connected component to be dead, and finally will be produced one connected component. So at this stage, we can see there is loop. There is loop with the empty region inside in the middle. So it will be referred as a hole. So at here, another topological features appear, and it will be referred as the topological feature hole, and the birth point for the topological feature hole, which represented by the red line here, will be equals to 4, and the epsilon value will be increased. The red line and the black line also keep increasing until epsilon equals to 5.66. The two to simplex is appear, filling up the hole that previously appear. So at here, we will say that the dead point for the holes feature will be at 5.68, and leaving only one connected component. So if we increase the epsilon value until 6, the one connected component is still here. So the left side for each line, which the black line refer to the connected component, red line refer to the hole, will be referred to the birth point, and the right side will be the dead point. So another representation of the persistent homology would be the persistent diagram. So persistent diagram is a simpler representation compared to the barcode. We have a 2D graph here with x-axis the birth point, y-axis the dead point, and the black dot will be referred to the connected component, and the triangle will be represent the whole. So here we have the multiplicity tree. So multiplicity tree refer to the 3 connected component, 3 dots, 3 connected component with birth point 0 and dead point 4, which refer to the 3 line here that stop at 4. And here will be the birth point will be equals to 4, and the dead point equals to 5.68 will be referred to the topological feature holes here, and the 1 dot component here will refer to the one connected component that have a birth point and dead point at birth point 0 and dead point 6. So that is the persistent diagram. Okay, now that's the idea of the persistent homology. You have a data set, you connect the data set, and you will extract the topological feature. So in this case, you have your raw data set, and when you connect the data set, you will have you will extract the topological feature, and in this case you will have one connected component and one whole. And actually this kind of data set is similar with object square, object circle, object rubber band, and also picture frame. All of these objects has a similar topological description, which is one connected component and one whole. Okay, now the formal term that we use to count the number of topological features will be the Betti number. So in this case, if we have one connected component, we will say the Betti number for zero-dimensional will be equals to 1. For the circle, we have a Betti number, one connected component, one whole. If for the sphere one, we have one connected component, 0 whole, and one void. And for the torus one, we will say that we will have one connected component, 2 whole, and one void. So the formal term to compute to count the number of topologicals will call Betti number. Okay, I would like to highlight something about epistemology for time series data set. So if you have a time series data set, one-dimensional time series data set, you have to take an extra step. Step to transform the one-dimensional time series into higher dimensional data. So you're going to use the Takens method. So from the Takens method, we're going to construct the one-dimensional time series into a vector with a time delay tau and every dimension m. So there are two parameters that you have to choose. You have to choose to apply the Takens method, which is the time delay and every dimension m. So now, the reason you need to transform your one-dimensional time series to higher dimension data set is to able to study the higher dimensional topological features such as holes and void. The holes exist at least in the two-dimensional data set, and the void and holes, the void will be exist at least in the three-dimensional data set. So if you want to study higher dimensional topological features, you have to transform your data set, one-dimensional data set, into higher dimensional. Okay, so this is an example for transform the time series for time series with length n equals to 5. We're going to apply the Takens method. Let's say we choose the tau equals to 1 and m equals to 3. So the first element for your new data set will be equals to y1 equals to x1, x2, x3. Y2 will be equals to x2, x3, x4. So this is your data set. So you're going to apply the Takens method in these five points of time series, and you're going to have a new data set in the three-dimensional, which is correspond to the many dimension, m equals to 3 and tau equals to 1. This is an example of the transformation of time series. One-dimensional time series, one-dimensional series. Let's say you have S1, S2, S3. You can see that it is actually a one-dimensional series. So we're going to apply the Takens method, and we're going to have a new kind of data set. So this is an example of the new of your reconstructed data set, which based on the Takens method. Based on Takens methods with the tau value, tau equals to 1 and many dimension equals to 3. So this is your new data set, and you're going to apply the persistent homology in this data set, which is in the three-dimensional data set, and you're going to have the barcode. So here we can see that the S1, S2 has the similar shape, and for S2 will have a different kind of shape, and based on the barcode we can see there are similar pattern for the barcode for series 1 and series 3, and the different one will be barcode for series 2, which is correspond to the shape of the data in the reconstructed data set that you have construct before. So that's how we reconstruct again the one-dimensional time series, and we perform the persistent homology. Okay, Dr. Fariha, is there any question before I proceed with part 3?
I don't see any question. So maybe you can just proceed, Fariha. Yes.
Okay, I'm going to proceed with the final part, which is HACA with TDA. Alright.
Oh, Fariha, ada one question from Syukur. Syukur is a PhD student. Okay. Salam Dr. Fariha, I have a question. Is it possible to apply Takens method if the number of component in each time series is different? Can you see the example, Fariha, in the comment? You cannot, yeah. For example, let me read for you. T1 is x1, x2, x3. T2 is x1, x2. So maybe he means the first time series is x1, x2, x3. The second time series is x1 and x2. And the third time series is x1, x2, x4.
Okay, so is your time series different with each other? We have you have three different kind of time series, is it?
Syukur, do you want to ask your question directly? Would it be easier to explain? Can you raise your hand so I can unmute you? Nak cari Syukur tak jumpa. Okay. He rose his hand. Okay, Syukur, allow mic. Okay, Syukur, oh, Fariha, your battery is running low. Ya, Syukur, saya dah boleh unmute, boleh bercakap?
Okay. Salam. So, yes. The punya time series is different.
Time series is different. So you have 3 one-dimensional time series.
Yes.
Okay, so you have to apply the Tankers method for each of the time series. So you will have 3 new data set. So you have to apply the Tankers method for each of the time series. Okay, so the Tankers method is actually for one-dimensional data. If you have one-dimensional data, it's not enough to study the topological feature. So you have to construct the one-dimensional into higher dimensional using the Tankers method. Okay?
Okay, thank you.
Okay, Syukur. I think that's all. And then Felix, did you raise your hand again? Felix, you want to say something?
Yeah.
Okay.
So I want to know, actually I'm using TDA my research work, and I want to ask whether the functions can be combined to make the in low dimensional, because I'm studying low dimensional, which is dimension 0 and 1. So can you combine algorithms in the performance of persistent homology to make for robustness? That is one of my questions. Possible?
Sorry, can you repeat the question? So the question about 0 and 1 dimensional for the algorithm.
Yes, in the algorithm, is it possible to combine algorithm in the aim of making the results more robust than when you combine, when you use just the RIPS complex.
Yeah. So okay, again, Felix. So you have so you want to combine the algorithm RIPS complex in order to study.
Yeah, in order to in studying the low dimension only.
RIPS complex for 0-dimensional homology only. You want to study the 0-dimensional homology based on the RIPS complex.
Yeah, I want to study the 0 dimension and 1 dimension only. That is the
okay.
Combining the algorithm, different types of algorithm, just 2 algorithms, 2 functions.
Different algorithm.
Yeah, with the objective of making for more efficient results.
By combining the algorithm, do you mean by combining the complex distribution complex?
Yeah, the functions. The functions are in the coding and using the software.
Okay. Philip, do you want to combine the RIPS complex with the other complex in the same data set?
Sure, yeah.
But okay, if you want to compute this first, if you want to compute this simplicial complex on the data set, you have to choose either one. Is it? So if you choose the RIPS complex, you're going to compute the RIPS complex on the data set and you're going to study the 0-dimensional, 1-dimensional. So if you want to study other simplicial complex, and by using another complex, for example, maybe you want to try the witness complex, so you're going to get another different kind of topological information. So maybe less number of the connected component, less number of hole. So if you want to combine the 2 simplicial complex in one data set, I think that will be, I think it is not possible because you have to study one by one. So it depends on if you choose the RIPS complex, you're going to have this kind of information. If you have, if you choose another simplicial complex, you're going to have another topological description. Does that answer your question? So
okay.
you want to combine the simplicial complex, I think you have to work one at a time.
All right.
Is that answer your question?
Yeah, no.
Oh, okay.
Though in literature,
Okay.
and TDA
Uh-huh.
can combine with machine learning from my literature. Yeah, I've seen some works, that combine some functions. In recent research, they discovered that combination methods is more robust. So they are tending towards combining more algorithm, though the computation is complex, and combine them in order to produce more robust results.
Okay, Felix, if it's possible, can you forward the paper to me?
Yeah.
Okay. So maybe I will understand most.
It's all right because it works also with machine learning. TDA can be combined with machine learning in order to, help classify the, in classification, especially in prediction of, extreme event like flooding. Actually, it can be applied in so many areas: flooding, earthquake, and so on, imaging, and so on, etc. So that is, I'm talking from literature. Yeah, thank you. Let me not take your time. Go ahead. Thank you.
Okay, thank you, Felix. Fariha, did something happen? I hope her computer did not die. Fariha? Okay, maybe we give her some time. About Felix' comment about combining the different methods of getting the simplicial complexes. Yeah, I think Fariha has some problem with her internet connection. So I think if you can define a new way to calculate the complexes, maybe using the RIPS algo and a new algorithm to combine it to become more efficient, it's possible to get a more efficient algorithm. But I don't think it's a very easy thing to do lah. That's why I don't think there is a straightforward answer.
Sure, it's not. Is that's what I mentioned? Is complex. It's a complex.
Yes.
Yeah.
And maybe we can work together in future to find a more efficient algorithm. And also, in terms of finding low dimension, 0 and 1, sometimes for some paper, I think we get comment that, dimension 0 is the components, right? And dimension 1 is the wholes, right? So 0 and 1, you don't, some people say that you don't need topological persistent homology or topological data analysis to get that, because you can get the wholes and the components just from simple network analysis, which is simpler. So there is that. And I personally think that the strength of topological data analysis is in the higher dimension. Felix, what do you think?
Okay. It's okay from my thinking. I think it's okay. I think it's when you are working on a higher dimension, it can now be integrated.
Cannot be what?
You can now think of the idea of integrating functions, trying to obtain a more robust synthesis results.
Correct. It is my opinion that probably the higher dimension, there is more to be found or algorithm to be proposed for the higher dimension ones, because TDA strength is in the higher dimension. That's my opinion.
Sure.
Okay, I'm not sure what happened to Fariha, but maybe somebody else has some opinion. Other people using TDA, siapa ada kat sini, Sabri or who's here? Sadiq or Lukman? Let's see. Najwa has done some simplices. Yeah, anyone want to comment? So, oh, Fariha is raising her hand. Oh, she doesn't have access. Okay. Okay, Fariha, welcome back.
Actually, my battery running already connect the charger, but actually the plug is not turned on.
Oh, yeah, I suspected as much. But it's okay. It's normal problem.
Okay.
Yeah. Welcome back,
Alright.
Fariha.
So welcome back, Fariha. Okay. Back to the Felix question. Can Felix send me the paper?
All right. I will.
Okay. Can? Okay. Alright. So which one? Okay. Okay. Are we done with the question, Dr. Fatima?
Yes, you can continue with part 3. Sorry, I was just waiting for you. I didn't notice that you couldn't get access. So sorry for that. Yeah. Okay.
Okay. Sorry. I apologize. Alright. So let's continue with the part 3. Okay. Let's say you want the third part. I'm going to show the combinations between the hierarchical clustering with TDA. So let's say you have a three data set. So data 1, data 2, and data 3. So how we going to cluster this data set by combining the hierarchical clustering with TDA. Okay, so we're going to, in the step 1, we're going to extract the topological features using persistent homology and record the topological features in bracket. In the step 2, we're going to compute the summary statistic of topological feature lifetime based on the barcode. And in the step 3, we're going to create the multi-dimensional data set based on the summary statistic. And finally, in the step 4, we're going to apply the HACA based on the multi-dimensional data set. Okay, this is an example of your data set, data 1, data 2, and data 3, which is in the 2-dimensional data set. So in the step 1, we're going to extract the topological features by using persistent homology and record topological features in the barcode. Okay, this is your data set. You have 4 points in your data 1, and we're going to perform the persistent homology in the data set that has the 4 points. So we're going to compute a distance between the points. So this is the matrix that show the distance between the points. So that will be actually your epsilon value. So 0.1 and 0.2 will be connect with each other at distance 3. 0.1 and 0.3 will be connect with each other at the distance 4.24. So let's start with the first stage of the persistent homology. For epsilon equals to 0, we have 4 connected components. So we're going to draw the 4 line here in the barcode, 1, 2, 3, and 4. And we go when the epsilon value increase to epsilon equals to 3, so refer back to the matrix. So we know that 0.1 and 0.2 will be connect at the distance 3, 0.1 and 0.4 will be connect with each other at the distance as the epsilon equals to 3. So we're going to draw a line connecting the points. So 0.1 and 0.2 connect with each other. We're going to draw a line here. 0.1 and 0.4 connect with each other. We're going to draw a line here. 0.1 and 0.1 and 0.2. 0.1 and 0.2 already connect. So 0.3 and 0.4 will be connect with each other. And 0.2 and 0.3 also will be connect at the epsilon equals to 3. So we're going to have a connected data set. And at this stage, we can see that the data set form a loop. Which is empty region at the middle. So we're going to have the birth of the topological feature hole here, and we're going to record in the dendrogram. So the birth in the barcode. So the birth point for the topological feature holes here will be equals to 3, and when we keep increasing the epsilon value, and at the epsilon equals to 4.24, refer back to the matrix. So 0.1 and 0.3 will be connect with each other at 4.24. So we're going to draw a line here, 0.1 to 0.3. So 0.1 and 0.3, we're going to draw a line here, causing the dead of the topological feature hole. So the two simplex here that appear at the epsilon equals to 4.24 have filled up the hole here that previously appeared. So the dead point for the topological feature hole will be equals to 4.24. Okay. Now, if we can increase the epsilon value until 6, then only one connected component will be produced. Okay, next for the second data. So this is your data 2, and we're going to compute the distance between the points, and we will know that the distance of the 0.1 and 0.2 will be connect with epsilon equals to 2, and 0.1 and 0.3 will be connect with each other at the distance 2.24, and so on. So we're going to construct the Bristol homology on the data 2. So this is your data 2 with 6 points at epsilon equals to 0, and the epsilon equals to 0, we have 6 connected components. So we're going to draw the 6 line. So 1, 2, 3, 4, 5, 6. So 6 line which refer to the connected component at the birth point equals to 0. So when the epsilon increase to 2, we will find we will have 0.1 and 0.2 connect each other at a distance equals to 2. So we're going to draw a line connecting the 0.1 and 0.2 here. So we have line combining the 0.1 and 0.2. We also have a line that combining the 0.5 and 0.6, and it is also connect at the distance equal to 2. So when we increase the epsilon value, we're going to, more point will be connect with each other and refer to the matrix at the epsilon equals to 2.24, 0.1 and 0.3 will be connect with each other. So we're going to draw a line correspond to the distance where the 2 points connect with each other. And when we keep increasing the epsilon value, more point will be connect with each other, producing a two simplex will fill up the loop that previously appeared. So we're going to record the topological features in the barcode here, and the black line will be represent the connected component, and the hole will be represent the black line will represent the connected component, and the red line will represent the hole. So let's proceed with the third data set. We're going to compute the similar way to extract the topological features. We have distance, we know where the points will be connect with each other, and we're going to record in the barcode. But for this case, for this data set, we don't have a topological feature hole. So only connected component is appear in this data set. So for this data set, we don't have a topological feature hole. Okay, now we're going to compute the summary statistic for the barcode. So we're going to compute the sum of all lifetime, average of all lifetime topological features, and maximum of all topological feature lifetime. So the lifetime refer to the dead point minus with the birth point, and for D minus B here will be referred to the lifetime of topological features, and K here in the formula will be referred to the dimension of topological feature. If the K equals to 0, it will be the connected component. If the K equals to 1, it will refer to the whole. Okay, now in the step 2, we will going to compute the summary statistic. The summary statistic will be the summation, average, and the maximum lifetime of topological features. Now, for the first summary statistic that I'm going to compute is the sum of the topological feature lifetime. So we have the barcode there for data 1, data 2, and data 3. And in the barcode, I'm going to mention that we're going to exclude the final connected component to avoid the dominancy in the result. So we're going to just ignore the final one, and we're going to compute the summaries, the summation of topological lifetime here by computing the lifetime for the connected component and whole. So sum 0 here refer to the summation of topological features for connected component. So the dead point here 3, so 3 minus 0, so the three topological features have the lifetime of 3. So 3 plus 3 plus 3 equals to 9. And similarly, we're going to compute for the rest of barcode by subtracting the birth point and dead point to get the lifetime, and taking the summation of the lifetime for all the topological features, we will get the summation of lifetime of topological features. So we're going to compute the summation for the topological feature character components and summation for the whole. So now next for the average. For the average, we're going to divide the summation of topological features by the number of connected component. So in this case, the average for the barcode for data 1 for the dimension of 0 connected component will be 9 minus 3 will be equals to 3. So for the next, we're going to compute the average for the next barcode for data 1 and data 3. And for barcode of data 3, we don't have whole. We don't have the whole. So the average will be equals to 0. Similarly with the summation will be equals to 0. So here, since it is an undefined, we just replace it with 0. And now we're going to compute the maximum of lifetime. So we're going to compare the lifetime of the topological features and pick the maximum one. Choose the maximum topological features which has the maximum lifetime. So we're going to compute the maximum topological features lifetime for each of the barcode, and we're going to have the information for the maximum topological feature holes and connected component. But for the barcode data 1, we don't have the maximum for topological feature holes, so we're just going to replace it with 0. And we're going to create the multi-dimensional data set based on the summary statistic, and we're going to apply HACA on the multi-dimensional data set. So here we have the multi-dimensional data set, which consists of the information of the summary statistic that we have computed before, which is the summation, average, and maximum for the connected component, summation, average, and maximum for the whole. And we're going to compute the HACA based on this multi-dimensional data set. So we're going to repeat the process of HACA, create the dissimilarity matrix, choose the linkage, and we're going to have a dendrogram. So this is an example for the dendrogram for the single linkage of HACA. We're going to have a result of data 1 and data 2 similar with each other, and the most dissimilar will be data 3. And I would say that it will be highly related to the topological description for the data set, where the first two data set have a hole in the barcode, but for the data 3 does not have a hole. So it can be said that the data 1 and data 2 more similar with each other compared to the data 3. Okay, next is example for the complete linkage. The similar result also, we get the similar result as for the single linkage. For data 1 and data 2 is more similar with each other compared to the data 3. And that's how we combine the hierarchical clustering with the topological data analysis. We're going to apply HACA based on the topological information. And here for the every linkage, similar result, we get the similar result, which is data 1 and data 2 similar with each other compared to the data 3. And that's the example for the hierarchical cluster with topological data analysis. Okay, now I would like to mention something about HACA with TDA. The example that I show you is based on the summary statistic of topological features. But it is not limited to the summary statistic only. You can explore more topological summary to analyze your barcode or persistent diagram. For example, you might consider HACA based on the Western distance or HACA based on the bottleneck distance. So the Western distance and bottleneck distance is used to measure the similarity between the persistent diagram. So let's say you have, this is your first persistent diagram with features in the blue dots, and this is your second persistent diagram with the red dots here. And you're going to match between piston diagram X and Y. We're going to take the minimum mapping between the two features, and we're going to calculate the maximum between birth point and that point. The birth point of the first feature minus with birth point of second feature, and we're going to compute the Washington distance and bottleneck distance on this persistent diagram that have been mapped between the two persistent diagram. Okay, this is one of approach that you could explore. If you don't want to explore in the summary statistic or typical features, you could explore HACA based on the Western distance and HACA based on bottleneck distance. And the other one, you could explore HACA based on the Betti sequence. So the Betti sequence count the number of topological feature at epsilon value. So let's say this is your barcode. You could partition your barcode into several into the sequences of filtration value, and you could compute the number of topological features at a certain value of epsilon. Let's say if you have at the epsilon equals to 1, you will have the number of connected component 1, 2, 3, 4, 5, 6. So 6 here, and at the epsilon equals to 2, you're going to have 1, 2, 3, 4, 5, 6 connected component, and at epsilon equals to 3, you're going to have 1 whole and 1 connected component, and epsilon equals to 4, you're going to have 1 connected component and 1 whole. So you could gather the Betti sequence information of the topological features, and you could use that information in the HACA process. Okay, now I would like to mention for the software. So there are many software that you can use to compute the hierarchical clustering and topological analysis, Bristol homology, and so on. The easiest one, the one that you could download easily, will be the R using the TDA package. And if you're familiar with the MATLAB, you could explore JavaPlex in the MATLAB to compute the persistent homology. And if you're familiar with the Python, you could use the Skid TDA and research in Python. But I would like to mention that if you need the code, if you want to play around with the code, with data set, with topological features and hierarchical clustering, I could provide you the code that I used to produce the result in the slide. You can email me and I will provide the code, but it will be in the RTDA package. So if you want the code, you could email me, and that's all from me. Okay, to Fatima.
Okay, thank you, Fariha.
All right.
Let's see if anyone else has any other question. I don't think so. Okay. If anyone want to ask question related to maybe Dr. Fariha's student experience or PhD experience, because for your information, Fariha, in the audience there are even undergraduate students that want to be inspired to continue to master and PhD level perhaps. So maybe you can comment a bit on that, or maybe your experience.
Well, okay. I actually done my PhD in 5 years with 29 days. I submit my thesis on the 5 years for a PhD, and I submit my thesis on on 29 September. So based on my experience for the undergraduate student or master student that want to pursue in the PhD, you have for some you have mentioned before, you have to have passion. You have to have passion to do research, because I would say that you need a lot of commitment to done your PhD, to do the research, and you have to spend a lot of time. But in my case, I took 5 years, 29 days to finish my PhD. So don't follow me. Try to finish PhD in the less time. And what I will share that you have to have a good relationship with your supervisor. Prosami really helpful with me. Dr. Fatima really helpful giving the advice and so on. Dr. Albi and Dr. Munira, and I always ask question if I have something that I'm stuck with. In PhD, is normal to have a point where you start with your research. You don't know how to move on. You don't know how to do it. That's why you have supervisor. You ask for the advice. You discuss your problem and so on. So for the undergraduate student, master student that want to do a PhD, I wish you for good luck. If you want to ask any more question, you could email me. I would really be glad to answer your question. And I think that's all for me. Is there any question?
Not for now, but I think they're waiting for the grad question maybe. Grad voucher question. Do you have a grad voucher question, Fariha? Yes. I think everyone is just waiting for this one to secure the grad voucher. Okay, so I repeat the grad voucher question. If you want to answer, please raise your hand. To raise your hand, you can go to the top part next to the chat button. There's a smiley with a hand like this, right? And then you can click the raise hand button right next to it, raise hand, or you can click Control Shift K to raise hand immediately. So right after Dr. Fariha say finish her question, and then you can raise your hand immediately and I will go to you for the answer.
Okay. So the question will be a very simple question. The diameter of vertices in its complex must be ... epsilon. What is ... So I repeat the question. The diameter. Sadik says student.
Acik ke Sadik ni?
Acik.
Repeat Fariha, repeat. Tak apa. Kita bagilah Chan. Okay, tak apa. Repeat je Fariha. Tolong repeat je sementara saya allow dia.
The diameter of vertices in its complex must be ... epsilon.
Okay Sadik, saya dah, awak boleh unmute tapi awak kena bagi jawapan panjang lebar dan jelas.
Yes, Sadik.
Hello. Boleh
Hello
dengar?
Sadik. Boleh.
Boleh dengar? Okey. Jawapan panjang.
Tak adalah jawapan yang jelas lah.
Jawapan pendek pun tak pasti betul atau tidak. Okey. At least epsilon.
Alright. Go Sadik.
At least
Apa?
epsilon. At least.
Wrong. Sadik.
Wrong.
Salah.
At least epsilon.
Oh, wrong.
At
Okay.
most.
It's open.
At most epsilon.
It's open to somebody else who wants to answer.
Oh my god.
Felix wants to answer. Sorry, Sadik. Okay, Felix, you can answer.
I think you call it TOA. I think radius. I think the distance. Is it the units? You are talking of the units?
Can you repeat again, Felix?
Okay.
Sorry?
Do you mean the TOA? The units of the measurements of the diameter? I think the units usually the unit of the distance.
No. I show that just for the audience to get how the points connect with each other, and the diameter one will be referred to the Ritz complex. So for the Ritz complex, the diameter between the vertices or between the points will be ... epsilon. And yeah.
Okay. Maybe. What was the question again? The diameter will be what epsilon?
Yep.
So the question is what epsilon? So Felix, do you have an answer? You said 4?
Okay, no.
No, he's asking question.
Oh, okay. So not answering. So
I want
Sadik
to understand the question very well before answering the question. So I
Okay.
provide the answer because I know the diameter. I don't know whether you mean the unit of measurement.
All right. So do you know the answer? Do you know the answer, Philip?
I did not understand the question.
Oh,
Not
okay.
understood.
All right. So that's okay. Philip was asking the question. So Sadiq said at least, right? So that's wrong, Fariha. Sadiq, what was your next answer?
Okay. Let me pardon the concept here. Okay. So
Okay,
what
okay.
I know that for a simplex to be built, okay, it should be the distance at least epsilon, means the circle should intersect each other.
That's actually correct, but
Yeah.
not totally correct for the definition of the Ritz complex.
Yeah.
So that's true. Every complex must be at least epsilon, but the
Yeah.
vertex must be connected at least epsilon. But for the Ritz complex, the definition will be more detailed. And I will ask again the question to get the detailed one. So the diameter of the vertex and Ritz complex must be dot epsilon. So this is the definition of the Ritz complex. But actually,
Is
I
it
think
is it 2 epsilon?
no, actually your second answer is the correct one.
At least.
Okay, so Sadiq already answered the correct one.
It's actually
Second,
at most
right?
At most epsilon. Okay.
Yeah.
Okay. All right. So for your information, Sadiq is another PhD student. But it's okay, Sadiq. Later you email me what Grab voucher you want, Grab food or Grab mine. Okay.
Okay.
All right. Congratulations. And thank you everyone for participating. Is there any more question for Fariha? Okay. If there is no question, can I ask a question, Fariha?
Okay, Dr. Fatima.
All right. Because I saw when you explained the HACA calculation very nicely, I realized that it will be exponential if you have many points, right? Because for each cluster, you have to recalculate points and more points and more points. So it would explode really fast, right? What is the maximum number of points that you have used so far to calculate, so I can get an estimation of how big like the data points can be to use HACA?
Wait. I think 196 for 16 year data set, which is monthly. I analyze for the monthly. So it involved for 16 years data set. So I think it will be about 196. It's really difficult to analyze the dendrogram for the hierarchical clustering when the data set have observation that in large number. And that's why if you have a large data set, people will be prefer to do the k-means.
Okay. There's comment from our undergraduate student, Fidaus. If it's at least epsilon, let's say for epsilon 1, then a point X may be connected too far from waypoints, which is not the goal. Fariha, you can comment on this. Yeah.
If it's at least epsilon, let's say for epsilon equals to 1, then a point X may be connected to far away points, which is a point X may be connected to far away point, which is not the goal. If epsilon equals to 1, if the data points will not be in the range of diameter equals to 1, then the points will be not connect with each other. So we're going to have unconnected points. So if you have 4 data points, you're going to have 4 connected components, which means that your data point is still not yet connected. But for those mean that a point X may be connected to far away point, I think the point will not be connected with the far away point. So that's why you have to increase the epsilon value until the circle go bigger and bigger. And when the circle touch each other or even intersect with each other, then we're going to draw a line between the 2 points. So the 2 points will be connect with each other. So in order to the point to connect with the far away point, we have to use a larger epsilon value, which refer to the radius of the circle. Okay, Rita?
Yeah. I think what Firdaus meant, he was justifying your answer, because that's why you say that Sadiq's first answer at least epsilon, yeah, betul. At least epsilon is
okay.
wrong, because if at least
Ah.
epsilon, then you can have very very big epsilon, and then you will connect to far away points, right? Which is not the goal. I think that's what Firdaus is trying to say. Meaning he understood the answer to the to the question, which is very good, Firdaus. And this argument why the answer tadi is at most. Yes, correct. Yeah, I think that's what. Thank you for the comment. Meaning, he understood the answer. Can you thank you, Firdaus. If you have any comments, put it on. What about very big data set? Why do you use k-means for that? What is the strength of k-means? K-means for big data set, Fariha, you were saying? Do you remember?
I think this is my personal opinion. I don't know, maybe Dr. Hafta have a different opinion about this. If you use k-means for the large data set, you will be able to see where the points close to each other clearly compared to the hierarchical structure. If you refer to the hierarchical structure, it's quite difficult because to observe the observation in the hierarchical diagram itself is difficult because it's too small, right? So the easiest way, if we use the k-means, we could identify the cluster based on the points that close each other. So the k-means will be focused to the position of the points in the point position in the position of the points in the cluster. So it's easy to determine the number of clusters based on the k-means if you have a large data set. That's my opinion. Maybe Dr. Hafta have a different point of view for a large data set.
Okay, so if I understand correctly, your opinion is HACA is more suitable for small data sets and not for too big. Yeah, okay, okay, got it. Yeah, because you need to visualize in order to find the clusters, right? Okay, thank you. If anyone, it seems that everyone is satisfied with your answer, and thank you, Fariha, for your presentation. Can I ask you to stay back a bit? I want to ask you some other questions about other things. But our session has ended for now. We can close the session with tasbih kafarah dan suratul as.